Swayam Prabha. Digital India. Educated India.
A practical line search type algorithm, the algorithm tends to work like this. So, let me write this out. So, you start usually with some say an alpha bar greater than 0. You choose a row between 0 and 1, and I will tell you why this row is needed. You choose your C1 you choose your C1 and C2, and then what one does is is that you search over alpha. So, what one does is you try let me say check if the wolf conditions are satisfied. So, at each iteration check if the wolf conditions are satisfied. Check if the wolf conditions are satisfied. If not, you try an alpha. So, you initialize alpha equal to some alpha bar. If not, change alpha to rho times alpha. So, what you are doing is you start with a large enough alpha, and then you keep backtracking to see where you can to see what would be if your wolf conditions are satisfied. Right? You keep, and you can keep repeating this until eventually the wolf conditions are satisfied. If satisfied, you define alpha k as alpha. Define alpha k as alpha, and the next iterate x k plus 1 is defined as x k plus alpha p k, right. And then and you take k as use reset k to be k plus 1. So, what happens then is, so your algorithm then effectively then takes you through these iterations where x k plus 1 equals x k plus alpha p k, where p k is a sequence of directions, and alpha k satisfies the wolf conditions at each k. So, this is basically so what we get therefore is is a sequence of iterates such that that are given by this recursion x k plus 1 equals x k plus alpha p k, alpha k p k, where p k is a sequence of directions and alpha k is satisfy the Wolf conditions. Now, what I haven't told you yet is how is this pk to be chosen. So, we've been silent on this particular topic, so about about what the choice of pk is. So, the pk is to be can be chosen in a variety of ways, and I will give you a general result here, but the main thing is that the pk should be a direction in which the function decreases. So, the simplest thing you could do for this sort of purpose is to simply look for take pk to be the negative of the gradient of the function. So, locally we are assured that whenever if we take a step in that direction, if we move infinitesimally in that particular direction, the function is guaranteed to decrease. So, pk can be taken to be the negative of the gradient of the function, but that is not that is not the only choice. One could do many other things to choose the pk. In fact, variants of this gives rise to various different types of algorithms itself. Okay. So, I will now also mention to you a sort of a generic sweeping result which tells us what sort of pks do line search algorithms actually algorithms actually converge. Okay. So, now define, so that brings us to this topic of convergence of line search algorithms. So, define cos of theta k as basically the cosine between the negative of the gradient of the function and pk. So, obviously, this kind of quantity is because, so it's I am taking the inner product in the numerator, negative of the inner product, and dividing by the norms of these two vectors. So, obviously, this is well defined only when the gradient, when these two vectors are not 0. So, pk is obviously a direction we are choosing. So, it is a non-zero direction, and gradient of the function is, if it is not should be non-zero, then this quantity is well defined. Okay. So, what is theta k here? Theta k is capturing the angle between pk and the steepest possible descent direction you could pick. The direction that you could pick, which gives you the the steepest most decrease in the vicinity of the function. Right. So, this is the so theta k is capturing that the angle between these two. So, the theorem, which we will not prove, but I will just mention to you, is this. So, consider any iteration of the form, xk plus 1 equals xk plus alpha k pk. Now, where alpha k satisfies the Wolf conditions W1, W2. Now, suppose f is bounded below. Bounded below means it has the infimum of f over Rn is greater than minus infinity and is continuously differentiable. suppose the gradient grad f is Lipschitz continuous on an open set containing the set L. Let us call this set L. What is this set? This set is called the level set. It is the set of x's for which f x takes value less than equal to f of x 0, where x 0 is your starting iteration. Starting or initial iteration. So, now what does it mean? So, suppose the gradient f is Lipschitz continuous on an open set containing this level set, where x 0 is the starting iterate. What does this mean? That is, there exists an L dash say greater than 0, such that gradient of f at x minus gradient of f at x bar, open set, let us call this open set N, less than equal to L times norm of x minus x bar for all x bar in this open set N. Okay. So, we can take pk to be any set of directions, and choose alpha k such that the Wolf conditions are satisfied. Okay. And suppose the function is bounded and continuously differentiable, and the gradient is Lipschitz in the set that we are considering. So, what is this set L? L is a level set, means that it is from starting take all the x's that give you a better value than the one that you are starting with. The one you are starting with is x 0, all the x's that give you a better value, a lower value than what you are starting with, that entire region is called level set. That's your set L. Okay. And so, we are assuming that the gradient is Lipschitz on that set. Then what does it say? Well, then it says then cos square theta k times norm of gradient x k squared, this summation is finite. This whole sum is finite. Now what does this mean? So, the claim is that if you choose your iterations this way, if your function has these properties and you choose your iteration this way in the way that is indicated, and your alpha case satisfy the Wolf condition, then this particular condition, this has to be finite. Now, this looks like a bizarre technical conclusion, but actually it says a lot in one sentence. So, since this summation this is an infinite sum, right. So, if this infinite sum is finite, what does that if that infinite sum is finite, then it means that the limiting value of limiting term here should be going to 0. So, in particular limit as k tends to infinity, cos square theta k times norm square of this is equal to 0. So, it says that well you are this limit goes to 0. Now, if you look at this limit, what is this limit? It has two terms here. It has the norm of the gradient of the function, and it has the the square of the cosine of the angle between the negative gradient and the direction pk that you have chosen. So, now this tells you something quite nice and powerful. It tells you that if I choose my pk in such a way, so if pk, so what does this mean? If pk is chosen so that, say, cos theta k is, say, always equal to some epsilon, okay, say minus epsilon, okay, rather, since you have already a minus sign there, this is equal to epsilon, say. So, if I choose my pk so that the cos theta k is always equal to some constant epsilon, which is positive, then in that case, in this limit here, this cos square theta k would always be epsilon, and it can jump out of the limit. And and then what we are left with is that the gradient of the limiting value of the gradient of the function should be 0, which means that xk converges to if xk converges to some x star, then the limiting value of the gradient of x star should be equal to 0, right. So, if pk is chosen in such a way that you are making that pk makes an acute angle, okay. If pk is chosen in such a way that pk makes an acute angle with the negative of the gradient, right. So, it has some component. What this means is it has some component along the negative, it has a non-zero component along the negative gradient, then you are guaranteed that the sequence of iterates actually get you to a point where the gradient becomes equal to 0. That means you are satisfying the necessary conditions of optimality. Now, this means that it's important here that this angle is equal, the cosine here is some epsilon equal, which is positive and remains positive. And so, the way we have done this is by choosing an epsilon that is independent of k. If epsilon also depends on k and starts decreasing to 0, then in that case the limit of this product being 0 does not let me conclude that the gradient is equal to 0. It could well be that this product, the gradient still remains positive, and yet this limit is going to 0. So, this condition is effectively telling you that the way to ensure that your gradient vanishes is by making sure that this cosine remains bounded away from 0. So, that means you should continue to make a non-vanishing angle, that pk should continue to make a non-vanishing angle with the negative gradient, whatever that gradient may be. Okay, so, pk, if it continues to make this non-vanishing angle with the negative gradient, then the gradient itself will go to 0. Right. So, the simplest way of ensuring that is to take approach to doing that is to take pk to be the negative gradient itself. So, then you are collinear with the negative gradient, and in that case you would obviously make your yeah. So, in that case this would actually go down to the angle would go the angle will the epsilon in that case will always will be 1, and then the gradient will be equal to 0. This kind of algorithm is what is called the steepest descent. Steepest descent algorithm. Now, steepest descent only ensures that you are taking the direction of the steepest descent at each point. That may or may not be right for you in the long run, in the sense that the steepest, what looks like the steepest descent at a particular point may not give you a sustainable decrease all the way down when you go further. So, you have to take into account also how the steep directions of steepest descent themselves change. So, so the ideal way is to actually take into account also the curvature of the function, and that those kind of that gives you a much richer class of algorithms. That but they are once again another class in this kind that I have mentioned. So, they so long as when you are designing these sort of algorithms, or when you are coming up with your iterate, so long as you make sure that your cosine of the angle is continues to be bounded away from 0, you should be fine, and you will be going to your iterates will take you to the to a point where the gradient vanishes. All right. So, with that I will stop this this lecture, and we will continue next time.